Welcome to a presentation of the workflow and results of our active learning image category labeling system. The system was designed to enable computer vision product category recognition on the basis of unlabeled bulk image data. My name is Philipp Scharpf. I'm from the University of Constance and the company BMT Business Meets Technology Switzerland. I'm presenting this work also on behalf of my co-authors and colleagues Hila Hong and Oliver Dürr from BMT and the University of Applied Sciences Constance. Imagine you have an e-commerce product catalog and you would like to build an app that allows for product image recognition. To train a machine or deep learning classifier model, you need labeled training data. Since it is tedious to label each individual image, it is very beneficial to accelerate this process using active learning. We have built a system that transforms the bulk of unlabeled images into labeled folders with up to 93% less clicks than a sequential sorting would require. This labeled data can subsequently be used to train the image classifiers. We will now discuss the workflow of the system and some results of our evaluation. The process starts with a pre-clustering, where the bulk of unsorted images is pre-sorted into folders based on their similarity. This can be done, for example, using k-means clustering on image encodings generated by a pre-trained neural network. Our evaluation showed that clustering could already sort around 70% of the images correctly, according to a manual reference sorting. However, after this step, the images are still unlabeled, so additional steps are necessary. After the clustering, the user can name the cluster folders. This generates labeled image data. If we have a look into the folders, we see that there are still images which are not sorted correctly, so we need to shift them into their appropriate folders. For small datasets, this can be already done quite fast and we are finished. For large datasets, however, we can save a large amount of time using an active learning strategy. One such strategy is the so-called uncertainty sampling, which identifies candidates a classifier is most uncertain how to label. These candidates are then recommended to the user to be labeled first, in order to maximally improve the model at each step in the labeling process. In our evaluation, we tested 3 different classifiers: logistic regression, multilayer perceptron, and decision tree, in combination with 3 different uncertainty measures: margin sampling, least confidence, and Shannon entropy. This yielded a total of 9 test cases. The user can execute a classifier and request a list of candidates using a specified uncertainty measure. In the view of uncertain candidates, label recommendations are provided to shift an image from the current label to the actual label, as specified by a reference labeling for evaluation purposes. If a user clicks on one of the recommended labels, the system provides further recommendations of additional images that can potentially be moved accordingly. After quickly scanning the list, the user can move a large number of images with just a single click, sometimes several hundreds at once. This bulk move is the decisive novelty of our system compared to traditional approaches and will be discussed in the following. Before presenting the results, we shortly present our evaluation metrics. The first metric is the number of rounds in our pool-based active learning cycle. Then we have the seen images that the human annotator is viewed during the sorting. We, of course, also evaluate the accuracy of the classifiers. We have the completeness percentage of the images that are labeled according to a manual reference sorting. We have the shifted number of images by the annotator or the automated computer algorithm evaluation. Also, we have the number of clicks by the annotator during the sorting process, and we calculate the savings achieved by using active learning compared to passive learning. Comparing the performance of our different combinations of classifiers and uncertainty measures, we see that the saved clicks percentage is quite high and the logistic regression classifier performs better than the other classifiers, the multilayer perceptron and the decision tree. This result is qualitatively also reflected in terms of the area under the learning curve. Let us now turn to our bulk shift novelty to decisively accelerate the learning process by recommending a large number of images that can be moved according to a previous shift. For each round, there is a significant number of recommended image shifts accepted by the user. Also in this case, the logistic regression classifier is performing best. Here you can see the mean purity of the bulk shift recommendation in the active learning cycle, which is up to 91%, meaning also that there is little entropy in the recommendations. In terms of the final accuracy after the active learning process, also the logistic regression classifier performs best together with the Shannon entropy uncertainty measure. However, in terms of the runtimes summed up over the active learning process, the decision tree clearly outperforms the other classifiers. We carried out our experiments on 4 virtual CPUs with 16 GB RAM. We evaluated the performance of our system comparing different combinations of classifier and sampling methods. In our plot, the completeness of the sorting is a function of the required clicks percentage. In our best test case, the sorting was complete after only 20% of the clicks. Here you can see a plot of the active versus passive learning curve started from the beginning of the sorting. You see that using the pre-clustering, you already start at around 70%. And then in some rounds between 5 and 7, the completeness is improved to more than 99%. Comparing our different combinations of classifiers and uncertainty measures, we see that in the best test case of the logistic regression, the sorting is complete after only 20% of the clicks. Computing the area under the curve as a measure for click savings, we see that the logistic regression classifier with either Shannon entropy or least confidence as uncertainty measure is most efficient. In general, the evaluation of our active learning recommender system demonstrates that it is possible to significantly accelerate image labeling. By iteratively querying the user the labels of those images with the highest classification uncertainty, the image sorting quickly achieves full completeness. For reproducibility, our dataset and the system's front-end and back-end, as well as the evaluation script for the automatic simulation of the active learning process, is available publicly on GitHub. I will now summarize our evaluation results. The logistic regression classifier combined with Shannon entropy uncertainty measure performed best in most of our evaluation metrics, but needed twice as much runtime as the decision tree. Using our novel bulk shift recommendations, we could significantly accelerate the active learning process by up to 20%, which can mean a lot of time for large datasets. Our test set contained 2,786 images, which we divided into 33 classes. In the future, we plan to test further classifiers and samplings and test them on further datasets, which contain more or less classes or images per class. I am now very much looking forward to our discussion.